right, kids, here comes section 811. We are almost done. We've got one more section to go, and then we can call it a curriculum year. This one is called the washer method, and it's a lot like the disc method, except it's got a hole in it. Ever played washers? You know, we've got those little circles with the inner circle being missing. Washers, you might remember what I'm talking about. So washer method is same as the disc method, but with a hole. So what does that mean for us? And what it means is that we have an outer radius, a radius that goes from the center to the outer edge. He's called capital R of X. He's my outer radius, minus my inner radius, a little r of X. He's my inner radius, outer minus inner. And what I have to do with these, remember how it's normally pi r squared? This one is pi capital R squared minus little r squared. Each of them are individually squared. And the mistake that a lot of kids make, you probably know what the mistake is before I even say it. It is, maybe I want to put this in red. It is not the same thing as r of X minus little r of X quantity squared. It is not that. Okay, so be careful, because that's the mistake a lot of people make with these particular problems. So it is the capital R squared minus the little r squared, and you also still have the pi. All right, so we'll talk about that. Actually, let's go to the formula. All right, so if I go down to the box, and then we'll go back to the problem. Sometimes you might see it this way, and I don't necessarily ever do it this way, but some people might. It would be pi times capital R of X squared with respect to X as minus the same integral a to b of pi times little r of X squared with respect to X. You can separate them into two separate integrals is what that's saying, and that's what they showed on the curriculum video. But really the way that we're going to see this is the second way. He put the pi out in front. You can put the pi out in front. I probably tend to leave it inside. Doesn't really matter. It is a constant. Pi is a constant. So you can put it out in front, or you can put it in the middle, inside the integral. But this is capital R of X squared minus little r of X squared with respect to X. So capital R of X is the radius to the outside of the object, and little r of X is the radius to the inside. You'll see in the pictures in a minute of the object. I said it on the last video as well for section 810. I do believe that the way that the curriculum video does this is a little bit more difficult than our way of using those representative rectangles. So all the rules that we've learned with those rectangles apply to these problems as well, in that they have to be perpendicular to what you're revolving around. And you'll see it's going to be real easy for you to pick up where the outer radius is and where the inner radius is based off of your representative rectangles. All right, so here we go. Let's try a problem. We'll go back to the beginning here. For this one, find the volume of the region enclosed by the square root of X and X squared, and it's rotated about the X-axis. So let me show you what this looks like. It's kind of interesting. You've got the picture right there, right? They gave you the picture for these. It's this. That part right in there. Now, it's not important for you to show how it revolves around, but if you were to, it comes down in here. This would be the part that revolves. And so now think about that. It kind of opens up like it's this is like a circular disc. So maybe like a bowl or something like that that would have an opening. So I now have a hole in the middle. This disc doesn't go directly to the axis that I'm revolving it around. I'm revolving this thing around the x-axis. And so here's what I have, and you don't have to draw this extra stuff. I'm just kind of showing you where it would land. Here's the part that's important to us. I'm revolving it around the x-axis. So from the x-axis to the outer part, to the outside, that's capital R. And from what I'm revolving around to the inner part, this part right here, that's my little r. Okay, so I have two representative rectangles with these guys because there's a hole in the middle that I need to subtract out. I need to know bounds. Bounds are important to me. So I can see this guy here is a 0, 0, and this guy up here is a 1, 1. I can just see that, and it makes sense here. Square root of 1 is 1, 1 squared is 1, so it kind of all fits. All right, so let's see if we can figure out our capital R. Look at your representative rectangle. What does it hit? What's the top minus the bottom? The top of it hits the square root of x. What's the bottom hit? The axis, which is 0. Down here, this is 0. That means capital R is the square root of x. What's your little r? Well, little r goes, top of it hits the parabola, so x squared. The bottom of your rectangle hits the axis again at 0. X squared minus 0 is x squared. And so now you have all the pieces to be able to put this together, because remember, it's the outside radius squared minus the inside radius squared. Capital R squared minus little r squared. So let's put the area together, and then we'll put the integral together. So my area is pi, and then I'm going to use brackets. I have capital R is the square root of x squared, minus little r is x squared squared. That's my area. Capital R squared minus little r squared. Let's put it into the volume and we'll simplify it as we go. Volume is my bounds going from 0 to 1 of pi. Could be on the outside if you want it on the outside. Just doing my area. If I square a square root, that's just an x. If I x squared squared, I multiply those powers. This is x to the 4th. And there it is with respect, close that up, with respect to x, and you're done. Now you could put that in the calculator, and sometimes we're going to calculate out what they are, but pretty much that's your story. So again, the big thing to remember is that it's squaring each radius individually, not subtracting first and then squaring. Okay, so squaring each individual piece is important. We've got one more example, and then we'll do a couple practice problems and call it a day. All right, find the value of this enclosed region. Again, they were nice to us and they gave us the picture. They don't always do that. So I am looking at this part right in here. Find the volume of this enclosed region rotated about the y-axis. Okay, well if it's around the y-axis, then it's going to come over like this. And again, you don't have to draw that. I'm just kind of giving you the visual. So representative rectangle has to be perpendicular to the y-axis. I'm at the y-axis. I'm going to the outside. This is capital R. I'm going from the y-axis to the inner. That's my little r. Let's decide what they are. Let's figure out their values. Capital R. Now this is right minus left. So if I go to the right, oh wait a minute, before I do that, I might as well, remember I'm doing this around the y-axis, I have to change these equations. So it's probably easier if I were to do that. Let's take a second and do that over here. I have y equals x squared plus 1. And I want to know what x is. So y minus 1 equals x squared. X equals plus or minus the square root of y minus 1. If I am at the second equation, I am y equals 2x plus 1. Bring the 1 over, y minus 1, divide by 2, that's my x. All right, so these are the two equations that I'm using based off of the functions that I'm given. So capital R hits the parabola. The parabola is this guy. Now, am I at the positive square root of this thing? I absolutely am. This is the positive side of this. So it's going to be the square root of y minus 1. That's the right-hand side. And the left-hand side actually hits at 0. Right? Hits on the axis itself. Which, by the way, in the next section, they're going to rotate around lines, kind of like we did in the last section. So this won't be a 0 for ones to come. So for now, we'll put it as a 0. Gives me the square root of y minus 1. That's my capital R. My little r is right minus left. Right is the line. This is the equation for the line, y minus 1 over 2. The left-hand side hits 0 again. So I end up with y minus 1 over 2. Some people like to write that as 1/2 y minus 1, whatever. It's, again, equivalent forms. It's all good. So now we're ready to put the area formula together so I can get to the volume. Area is pi r squared. Pi, capital R, square root of y minus 1 squared, minus little r, y minus 1 over 2 squared. And then, what else do I need? I need my bounds. So I'm looking at this, and you can see they kind of gave it to you right in the picture here. I have these 2 points. I'm using the y values from those, the y coordinates. This one's a 0, 0. Actually, no, it's not. It's a 0, 1. Ooh, careful of that. Right? This point right here is a 0, 1. This guy up here is a 2, 5. And so as I'm setting up my volume, now I have my bounds. My bounds are from 1 to 5. And I have my area, pi. The square root of y minus 1 squared just gets rid of it. So this is y minus 1. I guess I could put in parentheses. And then minus this line, y minus 1 over 2, quantity squared, dy. That's it. You found it. All right, we are going to look at just a couple of practice problems, and we will finish up with those. So if we're flipping, and the first one I picked was number 4. Number 4. I have the square root of x is my graph. I'm going to graph it actually on this box. Square root of x. Y equals 0, that's the x-axis, and x equals 4. Vertical line. Okay, so what am I talking about? I'm talking about this section right in here. I am revolving it around the y-axis. Well, the y-axis is here. That means it's going to come this way. I'm getting a giggle out of myself because when I drew my picture on the, you'll see on the answer key that I revolved it around the x-axis when I set it up. I did the problem correctly, I just drew the picture wrong. So anyway, FYI, when you see the practice problems on this section, yeah, my picture's bad. The work is correct. All right, let's see what I got going on for this one. I'm revolving it around the y-axis. So if I do that, the y-axis is here, perpendicular to it. Go to the outside. Right? There's my capital R. Little r goes from the axis, y-axis, to the inner part. That's my little r. Now I'm doing number 4, remember? That's the one that I'm looking at here. All right, let's figure out some bounds, right? We know that this guy's 0, 0. This guy up here, I'm not really sure what he is. Let's think about that. I know my x value is 4. What's the square root of 4? And you say 2, and I say, yup. This is the 0.42. All right, let's see what else we need. We need our equations to be in terms of x. So if I have y equals the square root of x, then x equals y squared. And I think that's it. That's all our pieces. So let's see if we can come up with the area. The area is pi r squared. In our case, that is capital R. Oh, we didn't say what they were. Capital R. Right minus left. Well, the right-hand side hits 4. All right. The left-hand side hits 0. That means capital R is actually 4. If I go little r is right my function, y squared, minus left, which is 0, gives me y squared. All right, now I have them. Now I got my capital R's and little r's. So area is pi times capital R squared minus little r squared. Put it together with your volume. Volume is the bounds being y's, so 0 to 2 of, let's see, I can simplify this as I go. 4 squared is 16. Y to the second is y to the fourth dy. Now the directions for these say, sketch the area, got it, revolve it around the axis indicated, find the volume of the solid formed, and leave your answer in terms of pi. So this one they literally want us to work our way out of. And what did I forget again? I forgot the pi. There it is. So here we go. I will have pi, let's antiderivative this. I have 16y minus y to the 5th over 5, going from 0 to 2. So I have pi. I have 16, if I put the 2 in, 16 times 2 is 32. 2 to the 5th is 32. That's my putting a 2 in. If I put a 0 in, 0, 0, I get 0. And so now I want to subtract these two fractions. Well, 32 is actually 160 fifths. So if I take 160 and I take 32 away, I've got 128 pi over 5, and that's my final answer. So for these, they do want you to take it the extra step and actually solve it out. But they want you to leave your answer in terms of pi, which means the calculator is not much of your friend for these. You're better off just doing your antiderivative and working your way through it. All right, two last ones, number 7 and number 9. Number 7. This one, for these problems, sketch the area, revolve it around the axis indicated, set up the integral that evaluates the volume of the solid by the revolution. You don't have to solve these. So we're not solving, we are just setting up the equation. Number 7 it is. I need to know what the picture looks like first. X squared goes like this, as we know. If you remember the cube root of x, it's a sideways squiggle, like this. Okay, so here's the section that I'm revolving. It's this guy right here in between those. You like how I just made my origin bigger so it fit with the picture? There you go. Now this one's a little bit trickier in that we have a lot going on in the picture because we're going to revolve it both ways. If I revolve it around the x-axis, then my representative rectangles, remember I have to be perpendicular to the x-axis, I'm going to have one that's this way, he's my capital R, and I'm going to have one that's this way, my little r. So we're going to start with that. I need to know my bounds for this, so I want to know where, and I'll come up here, where x squared equals the cube root of x. There are a few different ways that you can do this, but really if you think about it, what are your values that would do that? If x is 0, then both sides are 0. If x is 1, so this is 0, 0, and this is 1, 1. That's when they would be equal to one another. You could certainly square both sides and yada yada, or actually factor it out and work your way through it, but I think logic is easier for that guy. All right, let's see if we can figure out capital R, little r going around the x-axis as I've drawn them. Capital R equals top minus bottom. Now this time the top hits the cube root graph, and the bottom hits the axis, which is 0. Cube root of x is your capital R. Your little r, top minus bottom, top is the parabola, x squared, minus the bottom is 0 again, so you get x squared. Now with that information, you can certainly set up what your area would be. And your area would be pi, the cube root of x squared, minus x squared squared. There it is. Let's put it into our volume. X bounds are 0 and 1. Pi. And then I have the cube root of x squared. You can leave it that way if you want. You can also write it, you might see it as x to the 2/3 power. This one is minus x to the 4th power. And there you go. But we're not done with the problem yet, because now they want us to go and revolve it around the y-axis. Now you can draw a new picture if you want. I think what I'm going to do is change up my color. So this time a couple things have to happen. First thing is I've got to have everything solved for x. So if I have y equals x squared, then x equals plus or minus the square root of y. And if I have y equals the cube root of x, then I have to cube both sides. Y cubed equals x for this guy. So I'm using these two these two formulas to be able to do this now, because I'm going horizontal. So I need the new formulas. I've got the bounds already, so I don't need to worry about those. I do need to figure out what my capital R and little r are. All right, let's see. I'm going around the y-axis this time, so I'm going this way. Now hopefully you can see this different color. This is my outer bound. This one's capital R. And then my inner one would be just this little piece there. That's my inner one. All right, so I've got right and left here. I've got right and left here. Again, you could redraw the picture if you want to. But let's see if we can work it out here. My capital R. The right hits the parabola, which is now x squared, but it's not x squared. It's actually the positive square root of y minus 0. So it's the square root of y. Little r hits the cubic function. Cubic function is this guy, y cubed. And it hits on the left at 0 again. So he is a y cubed ultimately. Can I find the area? Sure. Pi, capital R squared, square root of y squared, minus little r, y cubed squared. There's my area. Put it in the volume. Y values are 0 to 1, just like they are for the x values for this one. And I have my area formula. Area is pi. Well, the square root of y squared is just a y. Y cubed squared is y to the 6th. dy. That's it. So again, I really, really believe that making those representative rectangles help enormously with this. Again, you can watch the video. The video does get a little bit more complicated with some of the explanations, I think, than the method of the rectangles. So last question I'm going to do is number 9. I thought this one might stump you a little bit. This is a typical kind of AP worded question. Consider the curve y squared equals 9 plus x squared. That's a sideways parabola because now it's y being squared and not x. And the line segment AB joining A of -9, 0 and B of 0, -3 on the curve. The curve and line segment form a bounded region. Find the volume of the solid generated when the region is revolved around the x-axis. Show the integral and then answer. So they want both for this one. They want a final answer for this. And this one's calculator. Well, the first thing that I do is I've got to figure out the picture, right? So before I even get to the picture, I know I have a line segment and I have this curve. Well, the curve I can draw. It's a sideways parabola. It's going like this. Okay, that's a little crooked. Maybe I can make it a little better. No, whatever. You get the idea. Okay, then there's a line of some sort for this one. And again, I can get this curve by making a little table of values, something like that, to be able to calculate it out. But the line is an issue. The line AB has 2 points. Do you remember how to come up with, and this is why I picked this one, do you remember how to come up with the equation of a line? Back in the day of, like, I don't know, 7th, 8th grade for you guys. So you have 2 points and you want to come up with the equation of the line. The first thing you need is the slope. Well, the slope is, remember the picnic table with the martini glasses on top, y2 minus y1 over x2 minus x1. So if I do that, I take negative 3 minus 0 over 0 minus a negative 9. Negative 3 over positive 9, I get negative 1/3. And then I have to take that point and, or that slope and one of the points to come up with. Now, some of you might do the y equals mx plus b, come up with the b, but in our shoes now, we can just use our normal point slope thing. Pick either point. I'm going to go with the lower numbers. Y minus a negative 3 is y plus 3 equals negative 1/3 x minus 0. That's our standard for tangents, so I might as well just use that guy. Which gives me y equals, I'm trying to get it to a y equals negative 1/3 x, swing this 3 over, minus 3. And so that's the equation of my line. Now I have the equation. They did not give me that, they just gave me information to get it. And so it turns out that this line looks like this. It goes through at the point and down here. Here's my line. Y equals negative 1/3 x minus 3. So what's the region I'm talking about? The region I'm talking about is this guy right here. By the way, on this, remember now I'm revolving it around the x-axis, which means I have to have my equation solved for y. So I've got this one solved for y. I need this guy. He's going to just square rooty. So plus or minus the square root. Oh, goodness. I'll let them leave a message. I have... Sorry. I have 9 plus x. Okay. So I've got my two functions. Let's do our representative rectangles. They would be from the x-axis to the outer side. That's this guy. He's capital R. And from the x-axis to the inner side. There's my little r. These coordinates are important to me. Now you have a calculator that's going to let you actually solve these if you wanted to. If I take my two equations and set them equal to one another, I get negative 1/3 x minus 3, that's y, equals plus or minus the square root of 9 plus x. Now you can go through your calculator and figure it out, but here's what it comes out to be, just for the sake of our time. 0, negative 3 is this guy, and this guy over here is negative 9, 0. Kind of makes sense, right? In the midst of that. This one, your y-intercept's negative 3, so you can see that that crosses through there. This one, if you let x equal negative 9, then y would equal 0. So either you can use a calculator or logic to come up with those values, but they're your points. Let's see if we can find capital R and little r, and then we'll go through and find the area and volume. So capital R is from top minus bottom, so from 0 minus, the bottom hits the curve. Now, is it the positive part of the curve or the negative part of the curve? This is the positive square root of 9 plus x. This is the negative square root of 9 plus x. So it's going to be the negative part, right? You're down below the x-axis. So negative square root of 9 plus x. This was a plus there. Well, that's a negative negative, so my outer radius is the square root of 9 plus x. If I take the inner radius for this guy, let me think on that for a second. Top minus bottom. Yeah, that's good. We're good. Little r is going to be top is 0, and the bottom is the line. Well, the line is negative 1/3 x minus 3. That's going to be a plus 1/3 x and a plus 3. And so now I'm ready to set up my area formula. The area formula is pi, and it is my outer radius, capital R, square root of 9 plus x squared, minus my little r, 1/3 plus 3, and 1/3 x plus 3 squared. And then I'm ready to put the volume together. Now I'm going to go up above to be able to do that. So my volume's going to be, my volume up here, since I'm running out of space. My bounds, now these are x's, so negative 9 to 0 of my area. Now can I simplify this as I go? Absolutely. Squaring a square root gets rid of it, so this is just a 9 plus x. This one I'm not going to bother. That would just be ugly, right? 1/3 x plus 3 quantity squared with respect to x. And then I put that in my calculator. A lot of times kids will put this in and forget in the end to multiply by the pi that you also have, so be careful of that. But when I put it in the calculator, plug that all in, I get an answer of 42.4115. And that's your volume. Okay? So that one was a little bit different because they did not give you the equation for the line. You actually had to calculate that out on your own. All right. Let me know if you have any questions. Shoot me an email. I'll see you in class. We have one to go. Sweet. See you then.